Today we want to look at two kinds of convergence, absolute and conditional convergence. So if we're looking at a series, if the series converges, even if I make all the terms positive, that is, if the series converges in absolute value, then the series is said to be absolutely convergent. We don't need all those negative terms to get convergence. Then we get absolute convergence, and that's the stronger one. It just sounds like a stronger condition. Absolute convergence versus conditional convergence. Conditional convergence means we need all those negative terms to get convergence. We got to subtract so that we don't just go to infinity. So that we describe that by saying the series converges, but the series in absolute value diverges. And that's when we call a series conditionally convergent. So the conditional part is we need all those negative terms to get convergence. We need all the negative terms to get convergence. We need all the negative terms to get convergence. So that's the something else. We need those negative terms for convergence. Our favorite example of this is the alternating harmonic series. The alternating harmonic series is conditionally convergent. We get convergence with the alternating series test, but we did the integral test and saw that the harmonic series by itself, without the alternating part, is divergent. So the alternating series, we use the alternating series test to show convergence. We use the alternating series test to show convergence, and we use the integral test to show that the harmonic series diverges. So what this means is that the alternating harmonic series only converges because of the alternating part. Just the terms going to zero, they're not going to zero fast enough. If we make half those terms negative, then we get convergence. So this raises a question. When a series converges, that means it has some finite sum. So why do we have a difference in absolute and conditional convergence? So that's the important question. Why the difference? This is the question that we need to be asking when we find out that there are two different kinds of convergence, absolute and conditional. why would we have two kinds of convergence? We know that if a series converges, that means it has a finite sum. So this is how we were thinking about a series converging. If a series converges, that means that the sum is finite. There are two kinds of convergence, so there has to be something that can go wrong in this sum is finite. We add up the values, we get a finite sum. What could go wrong? And what we start to pick apart is how infinity, one of the reasons that infinity is complicated is that it breaks our normal assumptions about how things are supposed to work. This is why we have calculus, because we don't intuitively understand infinity until we study infinity in great detail. Our intuition about infinity is terrible until we start studying it in great detail. So when we say we're adding a bunch of stuff up and we're coming up with a finite sum, we can understand that adding an infinite number of things, even if they're all positive, could result in a finite sum. Just think of 0.3 repeating, that's equal to 1/3. So it's easy to conceive of adding an infinite number of things and coming up with a finite sum. One of the things that's difficult to conceive is that how we add those things up could change the sum. If we have a finite number of terms, then everything works just fine. A plus B is equal to B plus A. No problem. And that works with any number of finite terms. So clearly, the sum is finite has got to have problems. Otherwise, we wouldn't bother having two types of convergence. So we have to understand why we have two types of convergence. To that end, we're going to appeal to the alternating harmonic series. We know that the alternating harmonic series is conditionally convergent. That means if I add up all those terms, it has a sum. Excuse me, let's consider the alternating harmonic series. So what we're getting at is if a series converges, then the sum is finite. We mean that a sum is finite, and so what could possibly go wrong? I'm not asking this question as kind of like foreshadowing, like in a movie when someone says, what could possibly go wrong? Or I'll be right back. I want you to stop, and while we're looking at this, think about what could possibly go wrong when we add a bunch of stuff up and come up with a finite number. Shouldn't that cause no problems at all? So let's consider the alternating harmonic series. The alternating harmonic series is conditionally convergent, so it must have a finite sum. Since the alternating harmonic series is conditionally convergent, the alternating harmonic series must have sum. That's our intuition for convergence. We add things up, it's finite, that converges. So let's let S be the sum of the alternating harmonic series. Let's go 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus 1/9, and so on. Let's just write a bunch of terms of the alternating harmonic series. This goes on forever. But this is a convergent series, so it must have some sum. I'm going to call that sum S. One of the properties of a convergent series is that if I multiply all the terms by some constant, the series still converges and the sum gets multiplied by that constant. So one property of series if a series converges and we have a constant, then multiplying all the terms of the series, we still get a convergent series. And we're just multiplying, we'll just multiply the sum by that constant. What this means is that we can factor out constants, even over infinite sums, infinite convergent sums. So that's what this means. So that is the distributive property applies to infinite sums.
Professor, is the 1 the constant in this example?
Infinite convergent sums, because otherwise the sum itself doesn't make sense. So I have S is going to be the sum of the alternating harmonic series. And I know we can multiply by a constant. Oh, my speaker is off. Pardon me. Let's see. Am I muted? Try again.
I just had a question in regards to the constant. Is the 1 value next to suppose the constant value in this example?
No, I'm going to multiply by a constant. 1 is just the first term.
Got it. Okay.
So alternating harmonic series is convergent. So 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. All the even ones are negative, all the odd ones are positive. Plus 1/7 minus 1/8 plus 1/9, and so on. This is all going to equal some sum S. So if I multiply everything by 1/2, I'll still have a convergent series. I'm going to multiply all these terms by 1/2. So I'm going to have a 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus, and so on. Since this is just 1/2 of the alternating harmonic series, I would just get 1/2 of the sum. The alternating harmonic series is convergent, so if I multiply everything by 1/2, the distributive property still applies because it's a convergent series. Now what we're going to do is insert zeros in every other before and after each term. So now we're going to install a bunch of zeros. So I'm going to put in a bunch of zeros. I'm going to add 0 to the alternating harmonics, this 1/2 of alternating harmonic series. So I'm going to start off with a 0, and then I'll have plus 1/2, and then I'll have plus 0, minus 1/4, plus 0, plus 1/6, plus 0, minus 1/8, plus 0, plus 1/10, and so on. So at this point, I have added 0 to the sum. I haven't changed the order when we added things up. I'm just separating them out by zeros. So here's where we're going to bring in another fact about series. So also recall that the sum of convergent series is also convergent. So if you have a pair of convergent series, then their sum converges. And moreover, the sum of the sum series is the sum of the series. The sum of the sums of the series? Or am I thinking the sum of a sailor? No, that's a song. That's different. So what we're going to do is I'm going to take my original alternating harmonic series and I'm going to add it to my half alternating harmonic series. So underneath my 1/2 S series, I'm going to add my S series. So I'm going to just line things up. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus 1/9 minus 1/10 plus and so on. Here we have two convergent series, the alternating harmonic series and my half alternating harmonic series. And I'm just going to add them together. 0 and 1 is 1. 1/2 minus 1/2 is 0. And then I get a plus 1/3. Minus 1/4 minus another 1/4 is minus 2/4, which is minus 1/2. 0 and 1/5 is 1/5. Plus a sixth minus a sixth is 0. 0 plus a seventh is plus 1/7. Minus an eighth minus another eighth is minus 1/4 because it's 2/8. 0 and a ninth is plus 1/9. 1/10 and 1/10 cancels out to 0. So what we should notice, let's see, I should highlight the gaps. Plus a half minus a half is 0. Plus a sixth minus a sixth is also 0. Plus a tenth minus a tenth is also 0. Notice that when I add these two series together, I'm still getting all the terms of the alternating harmonic series. They're just coming in a different order. So I'm going, instead of an odd, then an even, then an odd, then an even, then an odd, then an even, then an odd, then an even, I'm going an odd, then an even, an odd, then an even, an odd, and then the next three terms, we can continue following the pattern. All the odd ones are still positive, so I got 1, then a third minus a half plus a fifth, then a seventh minus a fourth plus a ninth. The next one would be an 11th, which will be positive. And then the 2 1/12ths will combine to make a minus 1/6. And then after that would be a plus 1/13. And then that would continue on. So notice that the sum is still the alternating harmonic series with the terms rearranged. So this sum this is the alternating harmonic series with the terms rearranged. We're looking at the alternating harmonic series with the terms rearranged. Instead of going odd, then even, then odd, then even, we're going odd, odd, even, odd, odd, even, odd, odd, even. But all the terms are still going to be there. All the odd ones are still positive, all the even ones are still negative, and we're not going to be missing anything. So instead of plus odd minus even, plus odd minus even, we're just doing plus odd minus even, plus odd minus even. All the odds are still positives, all the evens are still negatives, and we're not missing anything. And everything seems fine until we remember that if we have the sum of two convergent series, we can just add their sums together. Sum of two convergent series, we just add their sums together, where this is the alternating harmonic series, which sum is S. And we add, to get this rearrangement of the alternating harmonic series, we added half of the alternating harmonic series. And so now we have half again what our sum was before, but it is the same set of terms. We've rearranged the alternating harmonic series into a different sum. And that is weird. It's the alternating harmonic series with the terms rearranged. And that rearrangement has produced a different sum. So when we have a conditionally convergent series, addition doesn't quite work the way we think it does, the way we expect it to, the way we've programmed ourselves to believe. This idea that addition is commutative and addition is associative, we barely even mention it after, once we say that 2 plus 3 is the same as 3 plus 2. Once we've seen that, we're like, oh, addition seems to be commutative. Doesn't matter what order we do things. Until there are an infinite number of terms, and until those infinite number of terms is conditionally convergent. Addition stops working like we think it should. And it gets worse. Moreover, when someone asks you what the sum of a conditionally convergent series is, what you should ask is, what do you want the sum to be? Because there's some arrangement that will give you the sum that you want. And addition certainly is very strange. This is why we have two different kinds of convergence. Rearranging the terms of conditionally convergent series will produce a different sum. Absolutely convergent series do not do this. Rearrange the terms of an absolutely convergent series, and you'll always have the same sum. Any questions?
So what are like some like applications in like a career for this? Like computer programming or?
That's a good question. I hate to give you a cop-out answer, but there's no way I could possibly know. In my career for the last 20 years.
Okay.
And like I said at the top of this class, it would be really nice if we had justifications for everything, but like professional justifications for everything. But that's not what I'm about. I'm here to ask you to understand math. So I don't know.
Fair.
We
So
need
this
to
is just
I'm here to tell you how numbers behave. I hate to
Gotcha.
bail on questions, but a lot of times we do things in math classes and we set up these applications, like, right, we look at these there's a whole section in the chapter 8 about applications to physics. Physicists aren't out there doing that. When you're solving physics problems, you're not finding antiderivatives. I mean, there are some physics applications that will lead to trigonometric substitutions, but you're not going to be doing trigonometric substitutions to solve the problem. You know what I mean? This is why in chapter 8, the integration part just like dropped right into a black box.
Gotcha. Okay.
Here's the importance of asking, what is the purpose of this? When students start asking, what is the purpose of this? This is when I know I have come across something that we've internalized and deeply held, a deeply held belief, and we've run right up into it. And that's when we start immediately looking at it and saying, well, this is pointless. So, and don't feel like I'm picking on you. There are 20 people in this meeting and 19 of them are like, oh, dude, what? No, you don't, this is not how addition works. And what happened, and this should happen a lot when we're in deep into the education world, when we're educating ourselves. Eventually, we're going to find a deeply held belief, and some academic is going to come along and poke you right in it. It's like, oh, boop. It's like, oh, I believe this. I believe this my whole life. My parents got to me early, and this is what I believe. And then someone's going to come along and say, oh, yeah, but poke. What about this? And our brain is going to fight. This is just what happens. It's called the backfire effect. You believe something so strongly, and then when someone comes along and says, check it out, what do you think now? We don't say, ah, yes, well, addition clearly does not work like I thought it did. We don't just accept things that way. We fight. Our brain goes into that fight mode. And we don't look at this and say, ah, yes, new evidence has come along and I will now reevaluate my deeply held beliefs. That's not what happens. New evidence comes along and our brain says, no, F you. And depending on the situation, it's like, oh, well, that thing is questioning us. Let's kill it. And then you're like, oh, yeah, let's do that. You know what I mean? So great question. But honestly, I don't know. I've been just thinking about how cool this is for like the last 20 years. So my other cop-out version of that question is like, oh, I don't know. You tell me. Because there's this huge knowledge base that we're just trying to be introduced to. And I was like, oh, what have people done with this? And, 20 years ago, 20 years ago was still 2000. 20 years ago was still this century. So 30 years ago, maybe 40 years ago, it was much harder to be like, oh, well, why conditional convergence? But it's 2021. Oops, there we go. I put the wrong one in, but that's all right. It's 2021, so we can do this. Absolute convergence has its own entry, and I think conditional convergence does too. So if I can do even a third cop-out to a completely valid question. And the example on conditional convergence is the alternating harmonic series, because apparently mathematicians is the only one that we go after. So we're a lazy lot. You know what I mean? One of the analogies that I came up with for thinking about things like absolute convergence and conditional convergence is like, oh, I don't really know why, but I'm going for the 100% unlock in a video game. So I finished the main quest line, but now I'm going to do every side quest so I can get the 100% unlock. And sometimes we're just doing 100% unlock. All right, so the point of this is that things are very weird. We have two kinds of convergence. Absolutely convergent series will not do this to you. Rearrange an absolutely convergent series, you get the same sum. Rearrange a conditionally convergent series, you get a different sum. That's why the difference. That's why there is a difference. That's why we need a difference. Things are weird in conditional convergence. All right, so that's going to do it for today. I will see y'all on tomorrow, and we'll talk about a test that gives us absolute convergence all the time, except the times when it doesn't. All right, that's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.